everybody. I hope everyone's having a wonderful day. So last day I introduced you to the concept of a graph. So remember, a graph is a pair of V, comma E, where capital V is the set of vertices, and E is a collection of pairs of vertices, the ones that connect the vertices. They're called edges. So remember, I denote N to be the number of vertices, M is the number of edges. So last day I talked about different kinds of graphs, like undirected graphs, meaning a graph with like this that has only undirected edges, versus a directed graph or digraph that has edges that go from one direction to another, where we say, for example, if this was a directed edge from E to A, if I had an arrow here. So as a side thought, how can I represent any undirected graph in terms of a digraph? So all I have to do is think about this. Okay, the undirected edge represents, if I have A, comma E in my undirected edge, it means it could be either A or E, and that's equivalent to E, comma A, right? So what I can do is I can replace every edge in this graph with two directed edges, like this. So before I had an undirected graph, now I have a digraph. But now you can see that my pairs of vertices and my edges now can model the undirected graph. Do you see how? Well, now I could go from A to E or from E to A, just like an undirected edge. Now I must warn, if you use this kind of transformation, that you could technically be violating the original intention of the model of the graph. For example, those single edges had a very special meaning. By making this transformation, you might actually be talking about a very different graph all of a sudden. So I must give you caution to the wind that while this is a general construction where you can kind of go back and forth, where you can replace edges like this back into an undirected edge, it goes the other way. However, the issue is just that the graph itself might be modeling something that this construction does not actually represent. Okay? I thought I would give you that interesting relationship between undirected edges and directed edges, but caution to the wind. If you make changes to what the graph looks like this, you might actually be changing quite dramatically the relationships those graphs might represent. So one key concept in graph theory is the notion of adjacency. So what do I mean by this? Is if there's an edge connecting two vertices. When I mean connecting, I mean there's an edge like U, comma, V. If there's a U, comma, V here, this edge, if that exists, then we would say U and V are adjacent to one another. So it's a relationship between vertices. So I'll just say there is an edge, I'll use quotation marks, connecting two vertices. So oftentimes in adjacency, we're curious about, are they adjacent or are they not adjacent? Meaning that there is no edge that connects them. In the latter case. So if edge U, comma, V is in a graph, then vertex V is adjacent to vertex U. So this is all in relation to U here. So V can be one neighbor. If you think about the graph where I have all my adjacent vertices, you can think of these as neighbors, and all of those neighbors form a so-called neighborhood. But I'm not going to talk too much about that, but it's something you should be aware of. Eventually it will be something that you might encounter in your future studies. But the point is that there's just this adjacency that exists if there's an edge. And it's all in relation to u here, the first endpoint. So this nuance doesn't really matter too much in undirected graphs, but it does when it's a directed graph. So in a directed graph, V is adjacent to U if there's an edge from U to V. So I must stress that when I write it like this with a directed graph, all I'm saying is that there's an edge from U to V, and if that is the case, then V is adjacent to U. However, in directed graphs, this relationship is not symmetric. What I mean by that is that if there isn't an edge V comma U, you can't say that U is adjacent to V. That only is the case if an edge V comma U existed in the graph. However, this notion kind of dissolves when you think about an undirected graph. In an undirected graph, G, an edge U comma V, like this, in G implies U is adjacent to V, and V is adjacent to U. So it goes both ways when it comes to an undirected graph. So this notion of which order they're in dissolves completely. So let me draw you a picture. So I'm just going to draw the same graph I had last day, and we'll ask questions about adjacencies. Question: which vertices are adjacent to A? Well, they're B, C, F, and E, right? So you would say all of these vertices are adjacent to A. Likewise, you can say that A is adjacent to E. You can say A is adjacent to F, and so on. It's very simple. If there's an edge that exists, then you can say that they're adjacent. So I could say that A and F are adjacent in G. So in contrast, if I were to make these edges directed like this, so now if I'm considering a digraph, which I've just created an arbitrary digraph. So this has nothing to do with the first thing I showed you. This is just another graph. I've changed it by changing the edges. So now the edges have a different meaning. So which vertices are adjacent to A now? Which ones? Is this adjacent to A? No, right? You got to think about it. Okay. We know that edge exists in this graph, right? So we can't say that A is adjacent. Can we say that A is adjacent to E? Yes, we can. Can we say that E is adjacent to A? No. Because we know that this is not true. However, there's an edge from E to A. Okay? So which ones are adjacent to A? So which directed edges? C and F. So you could say that edges or arcs or directed edges, I should be more precise, directed edges, C and F are adjacent to A. Okay? So that's really all adjacency is. So let's talk about another notion. It's called incidence. So oftentimes we need some way to talk about if two edges are adjacent or beside each other, that they're connected at a common endpoint, or we want to relate an edge to a vertex or an edge to vertices, or edges to vertices. We use this notion of incidence. So I'm going to say two edges are, I'll give them names. Let's give these guys names. E and E prime are incident are incident if at least one endpoint of E and E prime is the same. I.e., this is the phrasing you would often use if we're talking about two edges. You can say E is incident with. It's incident with E prime. Now, there's another notion that talking about this is the so-called way you talk about it in relation to vertices. So this is in relation to two edges. So furthermore, in an undirected graph, sort of running out of space there. An undirected graph, edge U comma V is said to be incident on vertices U and V. So we'd use the phrase incident with to talk about two edges. You'd use the phrase incident on to talk about an edge in relation to some vertices for which one or possibly both are their endpoints, okay? So, for example, if I ignore the directions on these edges and just think of it as an undirected graph again. So if I asked you, okay, well, which edges are incident on A? You would say, okay, this edges, this edges, this edges, and this edges. All of these edges are incident on A because they share a common endpoint, all A. However, if I want to say, talk about two different edges, I could say that the edge E comma A is incident with A comma B because they share one common endpoint, A. Okay? So that's really it. I just got to talk about one notion involving directed graphs. In digraphs, an edge U comma B is incident from sometimes people call this leaves, like as in you're going somewhere, like I enter a room or I leave a room, okay? Is incident from vertex U and is incident to or enters vertex B. So in the notion of a directed graph, you have this notion of coming and going, okay? I'm running out of air, as you can see. So what would I say about what I was saying before here? I can say and this edge here, E comma A, it is incident from E, but is incident to A. Because it's leaving E and going to A. There, you see that? So I leave a couple more examples in the notes. You can more than welcome to look at that. So there's a couple other notions I want to talk about here. So for some somewhat more general structures in graphs, there's a few others I want you to be aware of. We won't be seeing them a whole lot. So the notion of a parallel or called multiple edges. Parallel or multiple edges. Parallel edges or multiple edges. These are sometimes called multi-edges. So So all this means is that there are two or more edges. Now when I say this, I mean it not in the sense that we're talking at the beginning of the lecture. I'm talking about two undirected edges or two multiple directed edges of the same kind when I say this. Two or more edges with the same endpoints. So what I mean by this is, imagine I give you an undirected graph. So I have two vertices, A and B. All I'm saying is that I have two undirected edges. They share the same two common endpoints. These would be referred to as multi-edges. And naturally, you would call such a thing a multigraph. But I'll save that for a moment. I have one more thing I want to define for you. It's a so-called self-loop. So a self-loop. Very simple. It's an edge whose endpoints are the same vertex. So for example, if I put an edge like this, where both the endpoints are B, then this is called a self-loop. So a multigraph it permits multi-edges, and typically it also includes self-loops and self-loops. So it's a far more general kind of structure for a graph than the ones that I've been showing you so far. In contrast, a simple graph is as follows. A graph with no multi-edges or self-loops. So is this graph simple? No, it has parallel edges and a self-loop. This one over here, is this one simple? Yes. Yes, it is. It has no multi-edges and it has no self-loops. So, unless otherwise stated, we're going to assume that the graph is undirected. And simple. So unless I bring up some other point, just assume whenever I talk about a graph, we're talking about an undirected graph that is simple. Okay? So whenever anything talking about a graph, unless I say something else, just assume that if I don't say anything else. Okay? So next we're going to talk about degrees. I don't mean like academic degrees. I talk about the notion of a degree of a vertex. Let us consider the degree of a vertex. That's supposed to be the, by the way. Let me fix that. The degree of a vertex. So imagine I give you a graph that looks like this. The tree is getting very excited about this. This is a little different than the one I have in the notes because I just feel like changing it up a little bit. So all I'm asking about is how many edges are incident on A, or how many are incident on B, or incident on C, or incident on D. So how many are on A? So what I'm going to use is I'm going to denote the degree using a function-like notation. I'll call it deg, like this. So I can have the degree of A is the number of incident edges on A. How many are there? 2, right? How about the degree of C? How many? A, B, and D are adjacent to it. How many edges are there that are incident on C? 3. So what's the degree of a vertex? The number of incident edges on vertex V, which I'll write as diagonally, like this. So there's also notions for digraphs called in degree and out degree. They're defined quite similarly. So there's in degree and out degree. So in a digraph, is the number of edges incident to vertex V. And this is denoted often with a dag with a minus sign as kind of like an exponent of V like this. So it's the number of incoming edges towards a vertex V. So it's the ones that are incident to the vertex. Naturally, the out degree is the same definition, except it's incident what? Incident what? Incident from. Same definition, just I changed it from incident to incident from. And it's denoted with dag with a plus sign of V like this. So it's a much more specialized version of degree. And instead, I just count up the number of edges that are incident to my vertex or incoming to my vertex. And out degree is the number going out. So I'm going to focus mostly on just degree itself, but I'll give you a couple of interesting facts about the degree. So I want to ask you an interesting question. When you look at this graph, and we computed the degrees of, say, these two vertices here, is there any kind of relationship we can draw from the degree of a vertex if I try to add up all these vertices with the number of edges? I can frame this in a very simple situation. Now imagine you're at a party, and say each one of these vertices represents a guest at your party. And you naturally ask, okay, well, what are the edges? The edges are going to represent a handshake between your two guests. So if you asked each one of the guests how many hands they shook, and you counted up how many there were, so if I asked guest A how many hands they shook, or that person shook, and then I asked B how many hands that person had shook, and so on, how many handshakes would they report back to me? Is there any relationship between the true number of handshakes that happened? So in this case, 1, 2, 3, 4, 5. 5 handshakes occurred. Versus how many I'm going to get reported back to me. Is there any relationship between them? Well, it's going to be quite intuitive. And this is a very cute but powerful result. And it sometimes creeps into all sorts of things. So this is called the handshaking lemma very often. So I'll refer to it as the handshaking lemma. So all it says is for any undirected graph, G comma E, that the sum of all of the degrees of the vertices, so I sum over all the vertices. So for each vertex in the set of vertices, I'm going to sum up each one's degree. It's going to be equal to 2 times the number of edges. I love this proof because it's a very simple counting argument. It works like this. What's the degree? Okay, what's the degree? It is the number of edges incident on a vertex, right? Now think back to my reporting of a handshake versus the true handshake. when my friend here, say this is me, and these are my friends. When I say, hey, look, I shook person C's hand, and I shook person B's hand, what is B going to tell me? Oh, yeah, I shook A's hand, and C's going to tell me, oh, they shook their hand. So notice that every single time, if I look at each one of the edges, what's happening? I'm double counting the edges. So, every edge is incident on two vertices. So by double counting, every edge is counted twice. In the sum and that's really that's it. So I'm just employing what is called a double counting argument. So I just observe that each one of the edges has two endpoints. I count it here and I count it there. So I counted it twice. How many times do I do it? Over all the edges. Therefore, the sum of the degrees is equal to twice the number of edges. So I should point out that there's a similar theorem that exists for directed graphs. It's quite similar for any digraph. G is equal to VE. That the sum, if you take the sum of all the vertices and you sum up all the in degrees of each vertex, it's going to be equal to the sum of the out degrees, which is actually equal to exactly m, the number of edges. I'm not going to prove this one for you, but the ideas are pretty similar. So that's all I have to say about degrees. This fact on the handshaking lemma will creep up every once in a while when we talk about graphs. So we're going to talk next about complete graphs or cliques. So a complete graph, which is often denoted as capital K subscript n, is an undirected graph. Where every vertex is connected to every other vertex. So what do I mean by this? So for example, K1 is just a vertex. K2 is two vertices connected by a single edge. K3 is a triangle, so so-called triangle, because it looks like a triangle. That's K2. This is K3. So notice every vertex is connected to its neighbors. Does everybody see that? Okay, now, sometimes people call this a triangle, or the triangle graph. So if I simply take K3 and I put another vertex here and I connect it to all of them, I get K4. So this is the complete graph on 4 vertices. So it's often how it's said. So complete graph on n vertices. So the keyword is on. And generally the construction looks like this. So imagine I have V1, V2. So remember V1 and V2, you connect them by an edge in K2, right? Okay, K3, you connect all the vertices, you get a triangle, right? Before, you would connect all the vertices, you'd get K4. And you can keep doing this. So V5, so the complete graph on 5 vertices would be where you connect that next vertex to all the other vertices. And you can keep this process going all the way until you have some arbitrary number of vertices where you connect that to all the other vertices. So this is the complete graph on n vertices. This is an arbitrary construction of how you can do it. So you take a vertex, then you connect it to all the other neighbors. Got it? So I want to ask you a very basic question. How many, actually it's not really, I will explain why it's basic. So I want to know how many edges does Kn have? So I want to know how many edges the complete graph on n vertices has. So I want you to think about this. Now I write down the proof in your notes, so take a look at that. But think about it. Each vertex is connected to, or is adjacent to, each and every other one of the neighbors, right? So it's connected to each of them. But this is true for each one of your neighbors too, right? So if I have 5 m edges, what is the number of edges the complete graph has? Well, I have one vertex. I connect that vertex to n minus 1 other neighbors. So if I start here, I connect an edge to how many neighbors? N minus 1 many. But each one of those, so I have n minus 1 edges for one vertex. I do this for all n of them, right? So it means I have n times n minus 1, but using this double, notice that I'm double counting them as I'm doing this. So when I introduce another edge, I might potentially be putting back in another edge. So how many times can that possibly happen? Well, it's half that count. So this is the total number of edges Kn has, or the complete graph on n vertices has. This is the maximum possible number of edges a undirected graph, or a simple undirected graph, can possibly have. But what is this in terms of big O? It's big O of n squared. Do you see that? So you could just show that n times n minus 1 over 2 is big O of n squared. So the maximum possible number of edges you can have in a simple undirected graph is big O of n squared. How about for directed graphs? Well, let's use the idea I told you at the beginning of the lecture. I know each one of those undirected edges can be replaced with what? 2 directed edges. One going back, one going forth. Okay? So it means I'm going to double the number, which means that it's n times n minus 1. So it means that if I give you any simple directed or undirected graph, the number of edges, so the max number of edges in G is m is less than or equal to is big O of n squared, right? That's the whole point here. So this is the big point I want you to take away from this discussion. It's what a complete graph is and what is the maximum number of edges possible in a graph. It's big O of n squared. Does everybody see that? Okay, so a complete graph, or clique, is just simply a vertex where every other vertex is connected to it. So I have such a graph. We call it a clique or a complete graph. Got it? It's nice and simple. So next, let's talk about how we can explore a graph. So we're going to talk about the concept of a path and a cycle. So what's a path? Well, I'm going to first just draw a graph over here to make this a little easier to explain. I'm going to draw what is often called a wheel graph. I like to throw some fun looking graphs at you. The reason why they call it a wheel graph is because it has a spoke and then you have the whole wheel here. So I'm just going to label all of these. B1, B2, B3, B4, B5, B6, B7, and there's my wheel graph. So a path is a sequence. By the way, you don't need to know that that's a wheel graph. I just like to throw a little bit of graph theory here and there. A path is a sequence of adjacent vertices. In particular, I say a path is simple. It's simple if all of its vertices are distinct. That means they're unique. So just as an example, let me draw a path in this graph. So all I'm going to do is I'm just going to imagine I start at V7, and then I'm going to go V2, go to V3, then maybe go from V3 to V4, then back to V2. So I would list this blue path as V7, V2, V3, V4, V1, and then V2. So I give it as an ordered sequence. You can also list the edges, but I'm not going to worry too much about that at the moment. The big point here is that it's just a sequence of adjacent vertices. Key things that have to be adjacent. So it's worth noting that if this is for a digraph, you would have to keep in mind that you have to go only from edges where you go from to, never to from. Got it? Is this path simple? No, it repeats V2. In contrast, this red path I'm going to give you if I give you V7, V6, V1, and then maybe I went up to V2, then maybe I go down to V3, then I go down to V4, then I go to V5. This red path would be V7, V6, V1, V2, V3, V4, and V5. So the above one is not simple. This one is indeed simple. Notice it doesn't repeat any vertices. So from a graph theoretic standpoint, it's worth noting that the use of path I'm using here is sometimes called a walk. Hey, next, here we are. We're going to talk about what a cycle is. It's really quite simple once I describe what a path is to you. So it's just simply a path where the start and end vertices are the same. So it's sometimes called a closed path. So naturally, a simple cycle consists of distinct vertices. So, for example, if I go through V7, V6, then V1, then back to V7, this is indeed a cycle. Is it a simple cycle? Yes. In contrast, if I were to go from, let's pull my brown here. If I go from V7 to V2, then to V3, then V1, and then let's go V4, and then go back to V3, then V1, then V6, then V7. This is indeed a cycle, but is it simple? No, right? It repeats some vertices. Got it? That's it. Just be warned, whenever you talk about a digraph, remember the orientation or direction of the edge matters. So it means that you can't just be like, oh yeah, I'm going to go backwards. If the arrow is pointing in a certain direction, you have to go in that direction, okay? And oftentimes, a simple way of describing this is that the directed cycle must follow the edges in the same direction. Got it? It's really not too bad. Next, we're going to talk about some common structures and terminology. So, the next thing I want to talk about is so-called connectivity. So what does it mean for a graph to be connected? So we say a graph is connected. A graph is connected if there exists a path from each vertex to every other vertex. That's kind of small. It says vertex there. So is this graph connected? Yes, because I can give you any one vertex here, and I can show that there exists a path. So for example, from V2, so I could go from V2 to V7 by following this edge, or I could go through a whole bunch of edges. There's just some path. That's the point. Now there's, in digraphs, there is a much stronger notion. So there are two notions of connectivity. So the first one is called weakly connected. The first one is called weakly connected. So it's the exact same definition I have up here. So it's the same as above. Except replace all directed edges with undirected edges. So what I'm saying is if you give me a graph, it's a digraph, you're just going to ignore the direction of the edge and just treat it like an undirected edge. That's it. So if these had arrows on them, you would just pretend the arrow doesn't exist and it's just an undirected edge. So if that is true, then it's called weakly connected. Naturally, strongly connected. So strongly, in contrast, strongly connected it means there must exist a directed path from each vertex to every other vertex. So, by the way, what would you think you would call a graph that is disconnected? Disconnected, right? So if there was another vertex out here that was on its own, sometimes it's called an isolated vertex. It has degree 0. There's no way I could get to this isolated vertex. If it is not connected, it is called disconnected. And in these cases, you would just say, oh, it's not weakly connected or not strongly connected. Got it? It's really straightforward. Okay. Next. As you can see, I'm giving you a lot of terminology for a reason. It's because we're going to either, I want you to be aware of it for future studies, or we're going to use it. So you can think of this as a short primer on graph theory. I'm just kind of giving you the basic language and discussion that we're going to use. Okay. So in the notes, by the way, I give an example of this distinction between weakly and strongly connected. So just take a look at the notes. I give you a figure showing one where it is weakly connected and strongly connected. But you can very easily see how you can turn it into something that is not strongly connected. So next we're going to talk about trees. Now we've talked a lot about trees, but I'm going to give you a broader definition of what a tree is from a graph theoretic standpoint. So it's a connected graph. Now we know what that means. A connected graph that has m is equal to n minus 1 edges. Remember, we proved that actually earlier in this term, right? Earlier on, we showed that the number of edges is always one less than the number of vertices, right? That's a tree. That's one definition for a tree. Now, I'm going to give you several equivalent definitions of a tree. You can actually prove each one of these using one of or the other of their equivalent definitions. So you can prove these all in a big chain. So below are several other equivalent definitions. I'm going to give you a series of equivalent definitions for a tree. I'm not going to prove them for you here, but I'm just going to state them as fact. So another way of writing what a tree is any two vertices in G are connected by a unique simple path. So how to interpret this? This means that if I give you any two vertices, there must exist a unique, meaning there's not more than one path from that vertex to the other vertex. That's usually a classic. So another one is G is connected, but if any edge is removed, the induced graph, I haven't talked about subgraphs yet. We're going to do that next time. The induced graph, so what I mean by this is, as a result of removing this, what the graph will look like after I do this. If any edge is removed, the induced graph is not connected. Which, if you think about it, makes a whole lot of sense. If I give you some tree, what should the tree look like? Well, it should have a unique path between any two. So if I get rid of an edge, then I'm going to have to disconnect that entire graph, right? Because now there's no unique path. I broke one of them. So G is acyclic. That means it contains no cycles. I'll say it contains no cycles. So there's no way I can find a cycle in it. And the number of edges is exactly equal to n minus 1. And one more, and I'm going to draw another picture or two. G is acyclic, but if any new edge is added, the induced graph contains a cycle. That's a handy property. So if I give you some tree, if I add an edge into it, it'll create a cycle somewhere. So these are all equivalent definitions of a tree. So you can start off with that one, or you can use any of these other ones. Sure, there's other characterizations out there. So let me just draw a picture of a tree, and then I'm going to give you one last definition, then we're going to stop for today. So imagine I give you some vertices. I'm not going to put labels on them. So the key thing I want you to observe is there's no cycles, and the number of edges is what? Is one less than the number of vertices. So this is a tree. You might naturally ask, that's strange. If I give you several trees, what is that called? A forest. It's a set or collection of trees. I should note that for any forest, you should know that this following property holds. That the number of edges is always going to be less than or equal to the number of vertices minus 1. So it's an inequality here. Why? Because it's not necessarily connected, right? So for example, the forest might look something like this. So notice each one of these is a tree, right? So this is a forest. So anyways, we're going to stop right here. We'll come right back and we'll talk more about graphs. So I'll say thank you very much and have some beautiful day. I'll see you later.